Hello everyone, welcome to our chemistry class. Today our topic is stereoisomerism. We know that. What is isomerism? Isomerism means they have the same molecular formula but differ in arrangement of atoms in the space. Okay, today we are gonna discuss about stereoisomerism. This stereoisomerism is also called spatial isomerism. So it is also a form of isomerism. Means here the molecules have same molecular formula and also they have the same sequence of bonded atoms, but they differ in three-dimensional orientation of their atoms in space or spatial arrangement of atoms. Means in stereoisomerism here the molecules means the molecules which we are taking in this stereoisomerism, they have same molecular formula. Along with same molecular formula they have same sequence of bonded atoms, but they differ in three-dimensional orientations. So this three-dimensional orientation is refers to the atoms in space or spatial arrangement of the atoms, means they differ in spatial arrangement of the atoms. So the molecules which are showing difference in three-dimensional orientations are called stereoisomers, and this phenomenon is called stereoisomerism. Okay, this stereoisomerism is mainly of two types, that is configurational isomerism and conformational isomerism. Means this configurational isomerism means based on the conversion, means whether it is convertible or not, it is again classified. See, if it is, means if interconversion is absent in this, means if it is non-interconvertible, then this stereoisomers are called as configurational stereoisomers. Means here interconversion is absent, means here it is not possible for us to interconvert this. So non-interconvertible isomers are called as configurational isomers. If it is convertible, means if it is interconvertible, so they are called conformational isomers. So interconvertible isomers are conformational isomers. Non-interconvertible isomers are configurational isomers. Again, this non-interconvertible isomers are classified into two types: optical isomers and geometrical isomers. Today we are going to discuss about this optical isomers. See, what is optical activity or what are optical isomers? Means the phenomenon of rotation of plane polarized light. Next I'll tell about this plane polarization, all those things. So just we should know this. Rotation of plane polarized light is optical activity, means it is the phenomenon of rotation of plane polarized light. See, chiral carbon, we know that the carbon to which four different substituents are attached, that carbon is called chiral carbon or asymmetric carbon. Means this chiral carbons or asymmetric carbon containing compounds exhibits this optical activity, and these compounds are called optically active compounds. And vice versa. Vice versa means here achiral carbons or symmetric carbons doesn't exhibits optical activity, that means they are optically inactive. Okay, let us see this. See, this is related to optical activity. See, assume it as plane polarized light. We are passing this plane polarized light via Nicol prism and polarimeter, means that is polarometer. Means if we have taken chiral carbon or asymmetric carbon, then here rotation is possible. Means for the rotation to occur, we should take only a chiral carbon. Chiral carbon containing compounds means optically active compounds. So if the compound which we have taken is chiral carbon, then only this rotation is possible. That rotation may be either in the clockwise direction. Clockwise direction means like this, means towards right side. So clockwise direction or right side, that is dextrorotatory. If it is towards the left side or anti-clockwise direction, that is levorotatory. Okay, see, if means this happens only in the case of chiral carbons or asymmetric carbons. See, if we have taken the chiral carbon, then here we does not come across any rotation, means rotation is absent if we take any achiral carbon or symmetric carbon. Okay, now we are going to discuss some of the important points related to this. See, already we said that if we take chiral carbons, then only here optical activity is possible. Yeah, now we will discuss some points that are somewhat different. See, there are some compounds, even though that compounds have asymmetric carbon. According to our point, if asymmetric carbon is present, then it should show optical activity. But there are some compounds, they have asymmetric carbon, but they are not gonna exhibit any optical activity. For an example, meso compounds. See, in this meso compounds, asymmetric carbon is present, but in the meso compounds, optical activity is absent. Example, tartaric acid. See, if we observe this carbon, if you observe the four substituents or four groups attached to this carbon, they are different. That means here it is a chiral, so it should exhibit optical activity, but here it is not exhibiting optical activity because here plane of symmetry is present, so it is not exhibiting optical activity. So this is one special case, so it is inactive. Similarly, racemic mixture means it also have the symmetric, racemic mixture also have asymmetric carbon. See, to this carbon four different patterns or attached, so that it is also asymmetric carbon. So here asymmetric carbon is present, but due to net specific rotation, so due to net specific rotation, it is also optical inactive. So this is a special case. So according to our point which we discussed, if what chiral compounds means here the chiral compounds show optical activity, but here even though these are chiral, they are not exhibiting optical activity. So this is a special case. Yeah, let's go to a second special case, that is here chiral carbon absent, but here optical activity is present. See, chiral carbon is absent but optical activity is present. Examples for this are allenes, spirines, biphenyls. Allenes, see, adjacent double bonds are present. So these are allenes. In this chiral carbon is absent, but here optical activity is present. In the same way, for spirines, spirines means two spiral rings are connected with the help of single carbon atom. So these are spirines. Spirines also shows optical activity. Biphenyls also shows optical activity. Now we are going to look at a simple and very important example related to biphenyls. See, what are biphenyls? Biphenyls means the two rings, means here the two phenyl rings are connected via single bond. They are called as biphenyls. See, here we have to observe. Here means top side both the substituents should be same. Means here if you observe, here it is x x, y y. Means for the biphenyls to exhibit optical activity, they should follow this, means they should have same substituents towards the top side and towards the bottom side. The question may be asked like this: which of the following biphenyl is optically active? See, in all the four options they have given biphenyls, so we have to observe the substituents attached. See here, iodine, of course here we had to look, no? So here the same substituents are same on the top side, but here they have not given any substituents, so this is not our answer. The same thing here also, here the same substituents are present, but however same substituents should be present on top side, so this is also not our answer. So the same thing here, they didn't mention any substituents, so this is also not our answer. If we observe this, see, here both the substituents are same, here also same, so this is the biphenyl which is optically active. So two different substituents should present on the same, see, this is a one ring, so to this one ring two different substituents are present, so here D is our option. Thank you. In the next class I am going to deal with means usually we get confused between small d small l capital D capital L, that one we are going to discuss in our next class. Thank you.